about what is a function in domain and range. You did domain and range over and over again last year, but the difference is in Algebra 2, you would do like one whole chapter of domain just on this type of graph, one whole chapter of domain and range just on this type of graph. And in Precalculus, they just kind of mix them all up, and people get very confused by it, so hopefully we can make some sense of it. And the next section, whenever we happen to get to it this week, is called 12 basic functions, which I think will help clear up domain and range. But we have some vocab today, right? Look at all this fun stuff we got. Function. Yes. What is a function? The math definition they give you is a function from a set D, domain, to a set R, range, is a rule that every value in D is different. To be a function, all x values are different. You learned that all the way back in Algebra 1. Who taught you Algebra 1? Mrs. Bai? Mrs. Rogers?
Yeah, I think that's her name.
I had Mr. Van.
She gave Lucas tuna one time, I think.
Tuna?
Yeah, for lunch.
Oh.
Lucas ate it for his food.
That's a weird story.
Yeah, she gave, Lucas didn't bring her lunch home or something. She gave her
Her lunch?
her lunch.
Oh, that's a good teacher. She's my friend on Facebook, and she always posts math stuff. Lisa Rogers, that's her name. See if she remembers you. She taught here 1 year. She taught like at Avon, and then she taught here 1 year, and then Avon took her back, so she left us. But she had 100% of her 8th graders pass CCA. I am recording. She should look up what nice things I'm thinking about her, and how she gave Lucas tuna. What? Yeah, that was you. It was the first time I think that we've ever had all 100%. Like there's always like one kid that doesn't pass. Domain and range. I pray maybe that you know that domain means the x values and range means the y values. When I was back in, I don't even know what grade I learned domain and range. What grade? I probably like 7th grade. You learned domain and range in pre-algebra. Who knows? 1947.
20 years.
Let's see.
12, 15 years.
I don't know. I don't know.
It'll be about
I'm 32.
Holy cow!
How old was I in 7th grade? 12?
13.
Oh, you're older.
13.
13? I'm young. I graduated high school when I was 17.
Or 13.
I think I was.
My brother's 12.
So 20 years ago. 20 years ago, I was in 7th grade. I think we just figured that out. I always remembered in 7th grade that if you put in alphabetical order, domain, D comes before R, range, and X comes before Y, so then you could always remember the domain is the X's and the range is the Y's. That's how I remembered in 7th grade. I hope now it's just in your head, domain and range, domain is X's, range is Y's, but you have to know that. That's the big focus of the day, domain and range. How about this next question? This is why I printed these out, so you can like circle the answer. Remember when your math questions were like circle the right answer? It says, of the 3 graphs shown below, which is not the graph of a function? Because why?
That's the vertical line test.
Oh, okay, your Mr. Rand taught you well. Definition of a function. X cannot repeat itself. If you draw a vertical line and it touches in more than one spot, that means that same X value is there 3 times. That means that the X repeats itself. But that is the shortcut in the vertical line test. I think there are 4 questions on your homework today that are pictures of graphs, and you just get to say, is it a function, yes or no, by the vertical line test. I wrote the vertical line test here for you. I said if y is a function of x if and only if no vertical line passes through the graph more than once. Probably Ms. Bai, Mr. McClure taught you with the vertical line test that you can imagine like your pencil is a vertical line, unless you have a crazy like pencil that's not a straight line. If you ran your pencil across the graph, anywhere that you stopped, that pencil could not touch in more than one spot. And sometime in the near future, I might ask you to explain to me in words what the vertical line test is. So you don't have to necessarily memorize this thing, but you need to explain to me what the vertical line test is. Be prepared for that. It's math class and I make you write. I know. Don't say draw lines on a graph. Like, that doesn't tell me what the vertical line test is. Right? And every year people like to tell me that this is not how you spell through. And I know, but it's your notes so you don't have to spell things correctly all the time, right? Drive through. They spell it like that. Drive through. All right, here we go. This is the important stuff today. Domain and range. At some point in this chapter, we should get a lot better at domain and range, that we can just look at this equation and we know what it looks like and we know what the domain and range are going to be. But today we're probably not there. If you are there, then that's okay. You don't have to draw a graph. But I want us to make a graph of this first, and then we'll talk about the domain and range. Does anybody remember what a square root graph looks like? And if not, that's okay. We'll pick some points. What would be a good x value to pick for this one? 2 is a great number. Because 2 plus 2 is 4, and the square root of 4 is 2. What else do you want to pick? Negative 4. Negative 4 gives me the square root of negative 2. And what's the square root of negative 2? Not good. Undefined.
He said negative.
He didn't say negative 1 first. He said negative 4. I heard him. No, we're going to choose negative 1. I like negative 1, because negative 1 plus 2 is 1, and what's the square root of 1? 1. 7. 7 plus 2 is 9, and what's the square root of 9? 3. Yes, actually. So negative 4 I can't pick. What's the smallest number I can pick without it being imaginary? Chase says negative 2. What happens when I plug negative 2 in there? And what's the square root of 0? What? If I don't want imaginary numbers, you agree 0 is the smallest number I can get under a radical. Which means you probably could figure out what's the smallest x value that you need without actually making a graph, because you can't have a negative under your radical. Let's make a little graph here. You don't really have to graph 7, 3 if you don't want to. I like to pretend that my graph goes to 7. Anybody remember what this looks like yet? 2, 2. Negative 4 I can't graph. Negative 1, 1. 1, 2, 3, 4, 5, 6, 7 must be out here, like this. Oh, that's a terrible graph I've made. And negative 2, 0. When we do section 3, I'm going to remind you of all the shapes of the graphs that you're supposed to know from Algebra 2. If we connect this, it should not be, it should be kind of smooth curve. Kind of goes like this. In second hour, Grady said, I said, anybody remember what this looks like? And Grady goes like this. And I said, I always say a square root graph should look like half of a parabola on its side. You agree with that statement? It's half of a parabola because it's like the top half, and it's turned on its side. We never have the full one graphed when we're talking about functions, because if the full parabola was graphed on its side, does it pass the vertical line test? No, that's why it's always either positive square root or the negative square root, because if it was both, then it would fail the vertical line test. Okay, so square root graphs kind of look like this. So now, looking at the graph, the domain is what x values are included. Or a nice way to think about it is, where does the x start or stop on this graph? It starts at negative 2, and then what happens? It just is going to keep going forever, but we're never going to pick a number less than negative 2, so you can write this two ways. We can write an integral notation. I would say starting at negative 2 to infinity. Or if you like set notation, you can say x such that x is greater than or equal to negative 2. Both are okay. Do you see how maybe you could have gotten that answer without having to graph that? Because look at this equation and tell me, what's the smallest number I can plug in there without getting an imaginary number? Negative 2. So you don't have to graph to find domain, but it's a nice way if sure that you can make a graph. The range is the y values. Also looking at the graph, where do the y values start or stop? And then do they go up or do they go down? This is the positive half, so they're going to keep going up, and this is going up really slowly, but eventually it would include all of them. So my range is going to be from 0 to infinity, or again, you could say y, because it's the range, such that y is greater than or equal to 0. To find the range without the graph, you have to know a little bit, which is why after we do section 3, I think it will be easier. But look at the domain value was negative 2. What was the y value I got when I plugged negative 2 in? See how that's where my range started? You do kind of have to know whether it's going up to infinity or down to negative infinity, but you can get those values without actually having to graph it. Okay? Do you remember doing domain range last year? Like with everything you did domain range? Okay. How about this one? And you notice I've typed in, like these are examples from the book. And the first one they just wanted you to find domain, and this one they just want you to find range. But I put domain and range because I think it's good practice to find all of these. So this one says f of x equals 2 over x. Anybody remember what those kind of functions look like? Let's make a chart. I'm going to pick the numbers for you. Negative 2, negative 1, 0, 1, and 2. When I taught Algebra 1, I always told kids to pick those numbers. Does that get you a nice range? If I let you pick your own numbers, people may want to pick negative. So what happens? When I plug negative 2 in here, 2 over negative 2, negative 1. When I plug negative 1 in there, negative 2. When I plug 0 in there, you divide by 0, your calculator says error, error, error. Or am I just blowing up? On my top 10 excuses not to do your homework, one of them is I divided by 0 and my paper burst into flames or something. David Letterman's. I should put it up here so you can read it while I'm trying to read it. I used to have it up here, and then people would pay attention to it instead of me, and then be like, what is this? What happens if I plug 1 in there? I get 2, and if I plug 2 in there, I get 1. Maybe we can tell what this graph looks like by just graphing that, and if not, we might have to pick some more. Can I just connect these and make a rectangle? If you're not sure, if you don't remember, what if I pick numbers getting closer, like between 1 and 0, like 1/2? What if I picked 1/2? I would get 2 divided by 1/2, which is really 2 times 2, which is 4. So this side's going up, right? Is it ever going to reach 0? No, if I just keep picking these fractions, it's just going to keep getting bigger. Remember what that's called?
It's called the asymptote.
Asymptote. And the same thing on this, like if we pick negative 1/2, this would be negative 4. So this goes like this. So if you remember what it's supposed to look like, you don't have to pick a lot of points. Sometimes people call these L-shaped graphs. I think that's silly because it doesn't really look like an L to me, but some people do that. I like to call them these kind of graphs.
Oh yeah, those.
You have to make the hand movement, kids. You're not looking. You're not watching. It's like a cool math handshake. I don't know how you shake hands or that. You have to hit me from back. Like this. High five that way. Again, if you remember when you have a graph that has x in the bottom, but it looks like this crazy graph, I call it a rational graph. The book likes to call this a reciprocal reciprocal graph, because x on bottom, you're going to have an asymptote. Where is x never going to get on here? To 0. So is my domain everything but 0? But 0. We have to write that mathematically. I don't know how Mr. McClure let you do things, but I'm making you write it the correct way. Yes, he did.
You taught us.
So I know he taught you. So this is where you might choose set notation, because if you want interval notation, you have to set up two intervals. Because I want to go to negative infinity all the way up to 0, and I got to skip 0. So I'm going to say negative infinity to 0. Is 0 included? No, it's not included. Remember, it's undefined as 0. It's an asymptote. So this negative infinity to 0 is this little section of the graph. And then I'm going to skip over 0. So I'm going to say union. Start back on the other side of 0 and go forever, right? To infinity and beyond. So that's kind of a lot of work. So this is where people say, that's ridiculous. I'll just do set notation, because guess what you can say? X is everything but 0. So you can say x such that x cannot equal 0. And that says the same thing that all that fancy stuff says. Huh? So you could graph this to look at it, but also look at the equation. Look at this equation. Could you have looked at this and told me that x can't be 0? Because why? You can't divide by 0. What if it was this? You don't have to write this down. What can't x be in that equation? 3, because you can't have 0 in your denominator. So if you want to make graphs, you can, but probably, who wants to graph, right? Nobody wants to make these graphs. So you want to learn how to look at the equation and tell me what x can't be, so that's your domain. Now the range, we'll talk more about asymptotes tomorrow. We'll review horizontal asymptotes. We're not going to get there today. But the range is what y can't be. Looking at this graph, what can't y be? Joe says 0. I almost called you Adam. Joe says 0, and that's true, because this is going to go up to infinity forever. This one's going to go down to negative infinity forever, but it's never going to get to 0. There's no number you can plug in here that would ever give you a y value of 0. So guess what? The range is the same thing. Shortcut way here with the set notation. You can say everything over y equals 0. Same way, the exact same. Yeah, everything but 0. So look for things that make x undefined, like square roots. Square roots are always going to have a restricted domain because you can't have a negative under your radical. Rational function, if there's an x in the denominator, you're going to have a restricted domain. So what if I gave you something like this? This is an add-on, it's not on your notes, so I don't know if you can write it there or not. But I'm going to say, what if I said, find the domain and range of I signed a TA paper, and the guy that's office called me and asked if I signed a TA paper because I think it was going to be. Very disgusting of his mind. That's sad. That's sad. But that's okay. Don't overthink these. We get so used to having restricted domain and ranges that we forget when we have something like this. Are there any square roots in this equation? Nope, so don't worry about imaginary numbers. Are there any x's in the denominator of this equation? Nope, don't worry about dividing by 0. This is a polynomial equation, which means, what's the domain of that going to be? That's a cubic function. -1. Is there anything x can't be in this problem? Should I plug in negative numbers? Could I plug in positive numbers? Could I plug in fractions? Could I plug in 0? So if x can be anything, what do I say for the domain? The majority of functions that you dealt with in Algebra 2 have a domain of all real numbers because they're nice, smooth curves. There's there's no asymptotes, there's no crazy stuff. Ooh, remember those step functions you did in algebra 2? The stair step functions? Oh, remember piecewise functions? Those are weird. But this is a polynomial function. The domain and range is all real numbers, all those without infinity signs. So don't forget that. I like to give you that sometimes to confuse you. To remind you that sometimes the domain and range is all real numbers. Okay. Continuity. We like to talk about continuous functions or not continuous functions. And so we say continuity or removable discontinuity. Discontinuity means not continuous. So those are some fancy, those should be some like spelling words there. There's so many vowels in there. Continuous, here's my definition of a continuous function. A continuous function can be drawn without lifting your pencil. If you can draw a graph without picking your pencil up, then it's continuous.
Do we write that down?
Oh, maybe. So we're going to pretend that there's arrows on this. This is continuous from negative infinity to infinity because it is a nice smooth curve. And the short way to say that is I could draw that graph without lifting my pencil. If you have to lift your pencil for any reason, it's not continuous. And we like to talk about the different ways that it's not continuous. And if you take calculus, we'll spend a lot more time talking about these discontinuities. But I don't know, it's not that important here. But we have something called a removable discontinuity. Both of these are removable. The definition of a removable discontinuity is it can be replaced with one point, also known as a hole in the graph. Do you remember talking about those last year, a hole in the graph? Holes, asymptotes, no clue? You're not English, thank you.
It has a hole in the graph. You didn't do that. That's doing this last year. Yes, we did. There's a point of this concept.
This is an example of a piecewise function. I'm not really going to get into that too much right now, but basically this one is undefined right here as a, whatever a is, it's not defined, but then there's that dot up there. But basically, if I could take this little dot right here, and I could move it down, and I could fill that in with one dot, it would now be continuous. That's what I mean by it could be filled in with one point. If you could take one point and fill it in, it's removable. Same thing over here. This one doesn't have the dot up there, but it still has a hole in the graph, but you could fill it in with one dot, and now it's continuous, right? That's one dot, a hole in the graph is removable. A jump discontinuity, I don't even think we need to write down what that is. You could say gap if you want. There's a gap in the graph, but it means your graph jumps, right? Like your graph goes to a point, and then it jumps to another point on the graph, so a jump discontinuity. That's also a piecewise function. This is the most common discontinuity that we did in Algebra 2. An infinite discontinuity means that there's an asymptote. And they say infinite because that asymptote, it's not just going to jump from one spot to the other. It's not just a hole in the graph, but it's never going to reach that point. It's always going to be not continuous there. It's going to keep getting closer to it on each side, going to infinity and negative infinity. All right, so I think the next one you get to circle the right answer again. It's so nice. Which of the following figures shows functions that are discontinuous at x equals 2? Which one is not continuous, discontinuous at x equals 2? Kind of got to get used to these little notation here, right? But this is saying, I don't even care that it's from negative 9.4. But x equals 2, that's a hole in the graph, so they just keep going. But we're going to say, this is the right answer, and we could even say that this is a removable discontinuity. I know, aren't you going to print them out? Just a lot of words.
get through all these notes.
We are actually. With time left over. Yeah, you just said amaze balls on the list, just so you know.
What's that? Baseball.
It's in the dictionary, it's not.
Baseball. So is YOLO. It's gonna be in there.
I don't think, just because it's in the dictionary doesn't mean you should use it in, like,
YOLO.
essays, right? Like, you shouldn't be like, this book was amaze balls.
It was an baseball.
I just want to say YOLO. Like, I still would recommend writing that in your English paper that you turn in.
All these buckets.
I don't think you should say that. You talked about this last year. Again, the math definition of an increasing function is that a positive change in x results in a positive change in y. That means as x gets bigger, y gets bigger. And I'm going to double page mine since you guys have your page right there.
No,
Oh, look, see.
that's like split scratch now.
I know, right.
EW3s.
Oh, that didn't help me. Oh, I can't make the words bigger. But increasing. As x gets bigger, y gets bigger. I say if you look at the graph, right, from smallest to biggest, if you do a little die on there, it's like you're walking up, right?
Yeah.
Decreasing means as x gets bigger, y gets smaller, and it looks like the graph is going down, right? Decreasing. Constant means that there's no change. As x changes, y doesn't change, and it's just a straight line, right? Constant's easy. On your homework, you have, which is the next example, you have to give the intervals kind of like this. So it says, where is it decreasing? And they said, there's no arrows on this, but it's implied that there's arrows here. I'm not a big fan of that. That they don't put arrows on that, because it kind of looks like it stops.
Yeah, that's incorrect.
It is incorrect. But they say that this is decreasing from negative infinity to negative 2, because this is going down. And then at negative 2, it changes to constant, because it doesn't change at all. And then from 2 to infinity, it's going up. They include that point where it changes negative 2 and 2. There's kind of a big controversy in math of should you include the point where it changes, because how can negative 2 be both decreasing and constant at the same time? How can it be both constant and increasing at the same time? With me on that? So I count either way. If you include it or you don't include it, I would count it right. So I don't care. Questions about increasing, decreasing, and constant functions? How can I make this more challenging? Look at the next slide. Oh my gosh. It says given x squared over x squared minus 1, tell the intervals on which g of x is increasing and on the intervals of which it's decreasing. When we're talking about increasing, decreasing, and constant, I'm talking about the x values, first of all. But what makes this more complicated than the pictures I gave you before is there's asymptotes, right? When you're giving me increasing values and decreasing values, you can't include asymptotes because those are not included in the domain. So you have to skip over those. So step 1 is, what are the asymptotes of this graph? And you can kind of tell that by looking here. You could also tell by looking at this, right? If you said what would make that go to 0, it would be negative 1 and positive 1. And I just start from the left and work my way over. So if I start at negative infinity, what's happening on this section of my graph? Is it increasing, decreasing, or constant? As x is getting bigger, what's happening to y? Increasing, decreasing, or constant is really the question. But I got no answers. So. It's increasing. It's getting bigger, right? It's going up. So I could say it's increasing from negative infinity to that asymptote, but it stops at that asymptote because it skips over it. So we're not going to include that. I'm going to say negative 1 not included. Because it's never going to reach the asymptote. Now skip over the asymptote and start the next part of your graph. If I go here, what's happening on this part of the graph? It's still increasing until when? Till 0. So it's still increasing from negative 1 to 0. Your book's going to put a bracket around 0. I always put a parenthesis around 0 because I feel like it's not No, it's an asymptote. Can't include asymptotes, they're not part of the domain. Then what happens? Skip over to asymptote, what happens with this part of the graph? It's also going down, which means decreasing, so I can say also from 1 to infinity. If you put the zeros in parentheses, I'm okay with that too. Notice I didn't put a U. It's not wrong if you put the U there, but we're not really, like, we're just giving answer. Like, you could have a bunch of different intervals. If you want to put U's there, you can. Just because you want to get time for it. Try not to maybe draw over your book like I just did in this picture. Is that it? No, almost done. One more second.
Oh, man. Oh, we got a couple. Yeah, last one.
Fill in the blank.
Fill in the blank. Come here, Chris. Fill in the blank. Last year in Algebra 2, you talked a lot about finding local max and local min, and I just wanted to make sure I talked to you about the difference between a local maximum and an absolute maximum. So what if we drew this little graph over here, and what if I said, like this? Remember graphing stuff like that last year? A local maximum is just any high point on the graph. It occurs where the graph changes from increasing to decreasing. Hey, that's what we just talked about, increasing and decreasing. In Algebra 2, I always talked about peaks and valleys when I taught Algebra 2, because at any high point on your graph, or if it's changing from increasing to decreasing, this would be a local maximum. Local meaning in that local area, it's the highest point in that section of the graph. As opposed to the absolute maximum. The absolute maximum is the highest point on a graph. And I said some graphs do not have an absolute maximum. This picture I drew, does it have an absolute maximum?
Yes.
No. No.
What about this side? Is it ever going to stop growing? Right? Because this is going up forever, it's never going to reach a maximum point. It's going to always keep getting bigger. But what if both arrows pointed down? Would it have an absolute maximum?
Yeah.
Yeah, like a parabola pointing down, right? That would be a local maximum and an absolute maximum. Same thing with a local minimum. A local minimum is any low point on your graph, and it occurs where the graph changes from decreasing to increasing. This would be a local minimum. In Algebra 2, you pretty much only talk about local maximums, so you kind of leave that word local off, but I just want to make sure that you know that's not the minimum of the graph. Because the absolute minimum would be the absolute lowest point on the graph. And again, on my picture over here, is there an absolute minimum to that graph? No, because this side goes down forever. Remember we talked about even and odd functions, like even functions, the arrows point in the same direction, odd functions. You get like disco, Mr. McClure did disco like that.
No, you never did.
He smiled a lot.
Even,
He just stood there and talked.
odd. Okay, be nice. Mr. McClure's my friend.
You guys hanging out outside school?
But we both went to Mr. and Mrs. Hendrickson's kid's birthday party. Does that count?
That doesn't count. Wait, like the
There
one
were lots
she
of
just popped
teachers.
out?
No, the one that had second birthday party. It's not his birthday yet. Oh, man.
He turns zero.
This is day 1. 3 through 9, all 11, 14, 18, 21, 24, 25, 26, 29, 34.
Okay, I'm gonna be up till 2 in the morning doing this.
No joke.
Wow.
That's your son's.
I fell asleep in class.
Just so you know that you don't have to graph these, but on the ones that say domain and range, if you don't know how to find the domain and range, you might want to check the graph out. But if you can just look at it and say, what can't X be? The directions on these sometimes say check graphically. That means they assume that you have a graphing calculator and you can do it algebraically and then you can check it on your graphing calculator. Most of you don't have graphing calculators, so you don't have to you don't have to graph these by hand unless you just want to graph it to help you. Does that make sense? If you don't have a graphing calculator and you would like to check these graphically, you can look online. If you just Google free graphing calculator, one will pop up, kind of like the one that I pop up on here, and you can type stuff in. Also, if you have a smartphone, there are lots of free graphing calculator apps that will graph things for you that you can check out. The one that I have on my phone is called Good Grapher. It's free.
Graphing apps on your phone?
Just one, Good Grapher. It's the only one you need.
Oh,
Yeah. And so anytime I need to graph something, I pull my Good grapher. There's a whole bunch of other ones. That's just the one that he recommended to me, and so that's the one that I have on my phone, and it's really good. And it even graphs in different colors, like my fancy one that we recommended.
You have like math.
Who's this guy?
It's a student, Grant Carr.